combination of internal resistances of V1 and V2. Then what is the use of connecting the sources in parallel? Potential remains same, but the current capability increases. In case of parallel combination, the net current given by the two sources is IL, which is a combination of I1 and I2. So net current capacity get doubled when you are connecting the sources in parallel combination. Similarly, we'll go for the combination of current sources. Current sources might be connected in series or in parallel. So first we'll discuss about the series connection of current sources. When you are connecting, that's shown in the figure, two current sources I1 and I2 are connected in series such that they both are trying to send the current in the same direction. Then the resultant current source is a combination of I1 and I2, which is having the current same as I1 and I2. That indicates the current sources are connected in series having same current sources are connected in series when they are carrying the same current. So here I1, I2 are connected in series where I1 is equals to I2 and the resultant current source will have the same current as that of the individual current source. Whereas if you are going to connect them in series such that the polarities are opposite, means I1 is trying to send the current in the upward direction, I2 is trying to send the current in the opposite direction, then the total current given by these two sources is I1 minus I2, which is found to be 0. That means they are trying to force the current in opposite sense. That's why the net current passing through the circuit is equals to 0. Now, similarly, we'll go for the current sources in parallel. When you are going to connect the current sources in parallel, you may have any value of current source, they may connect in parallel. Let the two current sources as shown in the figure. The figure 1 shows the current sources I1 and I2 are connected in parallel. Both are trying to force the current in the upward direction. The resultant current source is a combination of I1 and I2, which will have a current equals to I1 plus I2. So in parallel combination of current sources, net current is algebraic sum of current sources connected in parallel. But it will be algebraic sum when all are trying to force the current in the same direction. Now in the same figure 1, if both the current sources are passing the current in downward direction, then the resultant current source will also in a downward direction with the value I1 plus I2. Now we'll move towards the figure 2, where I1 is passing the current in upward direction, I2 is passing the current in the downward direction. In such case, the resultant current is either you may consider in upward direction, that time it will be I1 minus I2. If you consider the resultant current source in downward direction, then it will be I2 minus I1. So that indicates whether it is I1 minus I2 or I2 minus I1, it depends on in which direction you consider the resultant. If resultant is along I1, then it is I1 minus I2. If resultant is along I2, then it is I2 minus I1. Now, while simplifying the network, we need to deal with the AC circuits also. That's why we must know, prior to start with the simplifications, some fundamentals about the AC circuit, AC fundamentals. Like we'll consider an AC EMF and AC current. It is as shown in the figure. An AC waveform is shown which consists of cyclic in nature, where continuously repeating a sinusoidal variations, where all the AC potentials and currents are shown with the lowercase symbol. The instantaneous EMF E is given as EM sine of omega t plus alpha, or the instantaneous current is IM sine of omega t plus alpha. Beta. Why? Because alpha and beta are the initial phase for the EMF and current. Now, as this AC values, AC EMF goes on varying with respect to time. The equivalent DC value of the AC source is called as a RMS value. So the RMS value of EMF is Vm by root 2 and RMS value of current is Im by root 2. Generally, AC values are referred to the RMS values only. When you are saying the AC voltage of 230 volts and 50 Hz, this 230 volt is a RMS value. AC source of 415 volts and 60 hertz. That time 415 volt is also a RMS. So generally AC values are always referred with the RMS value. RMS value is nothing but DC equivalent value of AC voltage. Now as shown in the figure, AC EMF is varying with the cyclic in nature, where the maximum value from the mean position is called as an amplitude. The waveform is repeating itself. The one single interval of the waveform is called as a time period, and the 1 upon time period is frequency of the AC. Now for the AC circuits, we may connect resistance, inductor or capacitor across it. When you are connecting a resistance will offer according to the Ohm's law, it will offer a resistance R ohms, and it is R is the resistance which decides the current passing through the AC circuits according to the Ohm's law. Whereas when you are connecting inductor or capacitor, these are not the active elements. These are not the actively consuming the power. Not active, we can say they are not going to consume the power actively, but they are reactive elements. Reactive means what? They are storing the energy and returning back. But these components will decide the current according to the Ohm's law. So when they are deciding the current according to the Ohm's law, the resistance offered by inductor is called as a inductive reactance, which is measured in ohms, which is given by the symbol X with the suffix L as shown in the figure, which is equals to omega into L. So this inductive reactance is effective resistance offered by the inductor for the AC current flowing through the circuit. This inductive reactance will not consume the power, it will only decide the current according to the Ohm's law. That's why it is called as a reactance and not the resistance. But it is as per the Ohm's law, that's why it is measured in ohms only. The inductive reactance is positive, whereas in case of capacitor, the current decided by the capacitor as per the Ohm's law, it is applying a effective resistance which is called as a capacitive reactance, which is equals to 1 upon omega into C. The capacitive reactance is negative because the effect of capacitive and inductive reactance are exactly opposite. Now what is omega? Omega is the angular frequency of the AC source. As your frequency 1 upon time period is frequency, that is N or F, then the angular frequency omega is 2 pi into F or 2 pi into N, where N is the frequency of AC supply. Now in case of AC circuits, effective resistance offered by the AC circuit consists of R, L and C components is given by an impedance Z. The impedance Z is a combination of resistance and reactances. The effective resistance R plus reactance is given with the imaginary term, which is given as J XL minus XC. Inductive reactance positive, that's why XL minus XC, because capacitive reactance is negative. So net reactance is XL minus XC. Now this impedance is expressed in terms of a rectangular form, consists of real part and imaginary part. Real part is the resistance and imaginary part is the reactance. The magnitude of the impedance is square root of real part square plus imaginary part square, and the angle phi is tan inverse of reactance, net reactance divided by net resistance. That is, angle is tan inverse of imaginary part divided by real part. Now we are representing them in a polar form in terms of magnitude and angle. So always we need to, while solving the problem, we need to deal with the rectangular to polar and polar to rectangular conversion number of times. We'll go through one example where, as shown in the figure, impedance Z1 is given as 500 plus J12, where 500 is the resistance and 12 is the reactance. Both are measured in ohms. Now we are interested to convert this rectangular form into a polar form. So to convert into a polar form, we need to obtain in terms of magnitude and angle, where the magnitude is real part square plus imaginary part square, and the angle is tan inverse of imaginary part divided by real part. Here imaginary part is 12, real part is 500, and the impedance in a polar form is 500.14 which is the square root value, and the angle is tan inverse, which is 1.374. The angle is in terms of radians. So angle obtained is might be either in terms of radians or in degrees. It depends on mode in which you are going to operate your calculator. Similarly, let now suppose the impedance Z1 is given in a polar form. In polar form, it is given as 1.023, angle is 117.171 degrees. Now again, the impedance Z1 now obtain its real part and imaginary part. Now real part is magnitude into cos phi plus j, imaginary part is magnitude into sin phi. That is 1.023 cos of angle phi plus j, magnitude 1.023 and sin of angle phi. Now the impedance is coming around to be minus 0.467 plus j 0.91. These conversions no need to carry out manually. Every time find out the square root and tan inverse is a very time consuming task, but on your scientific calculators it allows us to directly convert a rectangular term into a polar form or polar term into a rectangular form, and which is regularly required by us, because when you are going to carry out the simplifications of the expressions where the expression consists of a rectangular form or the polar form of the various terms, then in addition or subtraction is possible with the rectangular form, and the multiplication or division is possible with the polar forms only. So depending on the need of the operation, you may need to convert them in rectangular to polar or polar to rectangular and utilize your LCs for it.